Okay, the last topic for this week is solving trigonometric integrals, which in which case it's helpful to have these identities up your sleeve. Sine squared plus cosine squared is 1. 1 plus tan squared is secant squared, which you can prove using the first identity. Sine of 2x double angle is 2 sine x cosine x. Cosine of 2x is cosine squared minus sine squared, which has these other two useful forms which can be derived using this first relation. And then from this relation, you can find relation for sine squared x being 1 minus cosine 2x over 2 and cosine squared x being 1 plus cosine 2x over 2. Similarly, there's formula for sine of sum and difference of angles and cosine of sum and difference. Then you have this other useful formula for sin x times cosine y, sin x times sine y. Bonus question is, these can be derived using this relation marked by star. So go ahead and try this. It's pretty easy to derive this equation. Okay, so these are just some results that you should know. We're going to jump straight into examples because that's the best way to learn about integration, is to do as much as you can and to develop an intuition. Say tan to the power 5 theta times secant to the power 7 theta. The identity that we know which relates tangent and secant is that 1 plus tan squared is secant squared. And also recall that the derivative of secant is secant tan. So I'm going to rewrite this as tan to the 4 times secant to the 6 times secant theta tan theta d theta. Furthermore, I notice that tan to the power 4 can be written as tan squared whole squared, which tan squared can be written as secant squared minus 1 whole squared. Now at this point I can do the substitution u equals secant theta because I have expressed everything else in terms of secant theta. And du, which is secant theta tan theta d theta, takes care of this term. And I end up with a polynomial in u, which is pretty easy to integrate. And then I replace it by secant theta. Now the next example, tan to the power 6 secant 4. In this case, I just recall that the derivative of tangent is secant squared. I break the secant 4 into secant squared and secant squared. I rewrite secant as 1 plus tangent squared, and I use the substitution u equals tan x. And again it becomes a polynomial, and in this case the substitution was tan theta instead of secant theta, so the answer is tangent in terms of tangent. Now you'll notice that these were very specific strategies, so you can have a general strategy for tan to the power m secant to the power n, where if the secant power is even, you break out a secant squared, right? Express the secant as tangent and use the substitution e equals tan x. That's what we did in the second example. And if the power of tangent is odd, then you have to do a little more complicated, where you break out a secant tangent for the substitution and you replace tan squared by secant squared minus 1. And then you use u equals secant x. For any other case, there is no general strategy, so you have to be creative. Also recall that the antiderivative of tangent x is log secant x, and antiderivative of secant x is log of secant x plus tan x. For example, finding tan cubed x. Tan squared times tan x. Tan squared is secant squared minus 1. This breaks down into two integrals, and for the first one, you can use u substitution to get tan squared x over 2, and the second is log of secant squared. Similarly, for secant cube x, you can use integration by parts. Secant x, dv is secant squared, gives you v is tangent, and du is secant x tan x. You follow through and you'll notice that this also ends up becoming a iterative integral. So you get two of the same terms on both sides, isolate them on one side, and you get 1/2. Lastly, last integral is a identity from the beginning, which was given to you as a bonus problem. So if you ever find sine mx times cosine nx, just recall these, in this case m and n, are not power but coefficients of x. You express them as sums of sine or cosine integrals, which are easy to find. And that's it. And then you're going to find attached worksheet 4. You have to evaluate these integrals using appropriate method. There's a reduction formula for log x. You just have to prove, which means apply the integration by parts and just follow through the process. Um, Part B here is challenging. Is So what you have to do here is you have to sort of follow through until you reach the end. All right. So you have to apply the reduction formula multiple times, and then look at the pattern. 6 is challenging. So there's only 6 problems in this worksheet. This is kind of challenging. You start with the reduction formula, but apply it from 0 to pi over 2. You show this inequality. Yeah, you may need some direction on this. If you do, let me know. And also Friday's study hall, I'm available to talk about these problems once you have attempted them on your own. Okay, thank you.